Okay, so we have briefly introduced acceleration. And how did we talk about acceleration previously? Good, I would agree, change in velocity, but we saw it on a graph. That's typically how we've looked at acceleration so far, is on a graph, right? We had a velocity versus time graph, and we said if an object is doing this, it has a change in velocity, which is acceleration. And typically when we use the term acceleration in everyday terms, we think of acceleration purely to be speeding up. But in all reality, it's any change in velocity. So it could mean slowing down or speeding up, okay? So describe to me what's happening in this velocity versus time graph. What's the person or car or whatever, what's happening there? Okay, they have constant acceleration, but say it in a different way. Are they speeding up or slowing down? Speeding up, and what direction are they moving? Positive. I know they're moving in the positive direction because they are above the x-axis, right? The x-axis on a graph like this would be 0 meters per second, which would mean they're resting. Okay? And do you remember that little rule of thumb I gave you about the sign for acceleration?
It's the opposite velocity.
Okay, it's opposite velocity when? There's a specific time that it's the opposite of the velocity. Oh, I have it actually on the slide. When it's slowing down. Okay, when my object is slowing down, the acceleration is in the opposite direction of the motion. So they have opposite signs. So an example here would look like this. Okay, on this red acceleration line, okay, on this red acceleration line, tell me what's happening in this second graph I have drawn right here. What's my object doing?
Slowing down.
Slowing down, and in what direction? Yep, good. They're moving backwards. They're slowing down in the negative direction. Yet, what is the direction of my acceleration there?
Positive.
Yep, I have a positive acceleration because my slope is positive, right? And we know that on a velocity versus time graph, slope is going to be our acceleration. So that matches our prediction. Today, we're going to do a bunch of math using that equation right there to help us prove this rule of thumb, right? And we'll be able to use the rule of thumb to make a prediction about what our acceleration should be. Okay?
Is that the big three?
No, it's not a big three yet. So I wouldn't even write this one down yet because one of the big three is a variation of this one. Okay, I'll show you what I'm talking about here. But this is the basic equation for acceleration. Okay, the little line over the top here just means average. You won't see me draw that because I don't want to, okay? And we always solve for average acceleration, so there's no need for me to draw that. But the line over the top just means average. If you see it in a book or something like that, that's why. Delta V, give me a specifics about what does delta mean. It means change in, but it means what minus what?
Initial.
Final minus initial. Final minus initial. Okay, so we could also write it like this. Acceleration equals velocity final minus velocity initial. And then are we ever really having a change in time, or do we just pretty much have time? Yeah, usually we go from 0. So I'm just going to put it in as t, right? I don't have a starting time and a final time.
I think watch this on your YouTube.
I will tell you that some books, and AP in particular, label velocity like this. V minus V sub O. Okay, and initial velocity, they say VO. That just means velocity at time equals 0. So it's same as my initial velocity. I am so used to teaching it with the F and the I. That's my preference. But you'll be familiar enough with the equations. I think you'll know what they mean. But a blank variable means final, and then that sub-0 means initial. Okay, so you might see that in AP questions written that way a little bit. I'll do my best, but I usually just prefer the final and the initial for VF and VI. Okay. What about the units for acceleration? Do we have a guess on that or a thought about what our unit would be? Meters per second.
Squared.
Per second, yes. Or we write it as meters per second squared. okay? What this is telling us, let's get an example here for acceleration. If my acceleration is 4 meters per second, okay? That tells me for every second that goes by, my velocity increases by 4 meters per second. So I'm traveling 0, then after 1 second I'm traveling 4, then after 2 seconds, now I'm up to 8 meters per second, then I'm up to 12, right? I'm speeding up at that certain rate. Okay, so meters per second. Technically, your acceleration could be any length divided by time, right? Kilometers per hour per second could be my acceleration unit. Is it ugly and cumbersome? Yes. But could it be valid? Yes, right? I could say that I have 2 kilometers per hour per second would tell me that for every second that goes by, my velocity increases by what? 2 kilometers per hour. Okay, so you see how that works? The most common unit is definitely meters per second squared, right? That's what we use for gravity, and so that'll be our most common unit. And the goal really when we're converting things to get to that unit. Okay, questions there? All right, let's look through a couple basic acceleration problems here. Okay, so we need our calculator out if we don't have that yet. During a race, a sprinter increases from 5 to 7.5 meters per second over a period of 1.25 seconds. What's the sprinter's average acceleration during this period? Don't let the word average throw you off, right? We're always going to calculate average acceleration, so that doesn't need to change the way we do anything. I'm going to encourage you to kind of start making a list of what these numbers mean in our problem. So tell me, what does that 5 meters per second represent? Initial velocity, so VI equals 5.0. It tells me I'm getting to 7.5, which would mean that is my final velocity. And it says over a period of 1.25 seconds, which would be my time. Okay. And then I'm looking for acceleration. So acceleration equals final minus initial over time. Okay. It's really common for you to just put the numbers and say 5 minus 7.5. Right? You just read them and put them in, but we got to make sure we're doing final minus initial there. So the numerator gives me 2.5 divided by 1.25 tells me I have an acceleration of 2 meters per second squared. 2 meters per second squared. Okay. Do we feel pretty comfortable identifying variables based on their unit alone? Right? If you see something with the unit meters per second, what does that automatically tell you that it has to represent? Velocity. And then you have to decipher, is it initial or final, right? But if we see something in just seconds, that tells me time. And if we would see a number in meters per second squared, that would tell us that's an acceleration. So we can see that and categorize those correctly. Okay. Problem. We were speeding up in the positive direction and our acceleration was positive, right? Because anytime we're speeding up, they match. Anytime we're slowing down, they are going to be opposite signs. Let's try this one. Marissa's car is moving at a speed of negative 28.6 meters per second. She slows to a speed of negative 24 during a period of 3.2 seconds. What is her acceleration? I will tell you this. We know there's a difference between speed and velocity, but from now on, they get used interchangeably a lot. So just count that as a velocity, even though it says speed. I do that on accident too, but I know they mean different things, but our vocabulary is used to the word speed more so than velocity. So they can be used, and in these problems, we are still treating it as velocity. Yeah.
The difference is velocity is displacement.
That's right, and speed technically uses distance, and speed wouldn't have a direction. So there's no way it could have a speed of negative 28.6 because I can't go slower than 0. So the negative has to tell me direction here. So the only reason I bring that up is because I will use it incorrectly, problems will use it incorrectly, so you can just use them interchangeably pretty much from here on out now that we know the difference. Anyway, okay. It tells me I'm moving at negative 28, so that tells me VI. My velocity final is negative 24, and my time is 3.2. Go ahead and plug that in and see what we get for our acceleration there. Oops. What do we do if we are subtracting a negative?
Add those numbers.
We're going to add them together, and so that gives me an acceleration of positive 1.4 meters per second squared. Does that match the rule of thumb that we talked about earlier? Right? Were we speeding up or slowing down here? I started here, then I went to here. So I was slowing down, and I was moving in the negative direction.
So you were moving closer to 0.
Right, right, slowing down, negative direction. So my acceleration then, I should expect it to be positive. Okay, and that's what we came out with, was positive. Okay, if I go back to the previous, so that just gives us a little bit of an expectation, okay? Let's look at the differences between velocity and acceleration. We need to remember that they're not the same thing. They are both rates. They tell us how fast something happens. But velocity tells us how fast the position is changing, right? Our displacement, it's displacement per second. And our acceleration tells us how fast the velocity changes. So they are both rates. That's something that they have in common, because a rate is anything per time. But then this one, velocity is telling us position, and acceleration tells us velocity. So why don't you try this one on your own? I see two kind of red flags here. Do you see any issues with this problem here? It says a car is moving 75 kilometers per hour. It comes to a stop in 5 seconds. What's our average acceleration? Okay, do you see a red flag?
Yeah.
What do you think?
Stop.
Okay, comes to a stop. Good, I agree. That is one part that's not a number, but it's important because it tells us something, right? It tells us my final velocity is equal to 0. What else is a red flag here?
We'll need to convert it to meters per second.
Right, kilometers per hour and seconds. We don't want to work with that. So I want to go ahead and put that into meters per second. If we remember our shortcut, it should be easy. Okay, do you remember that shortcut?
Times 3.6.
Divide by. It's going to be smaller. Yep, we're going to divide by 3.6 to get us to that shortcut to meters per second. Okay, so that means my initial velocity is 75 divided by 3.6. If I'm looking at sig figs here, which aren't that big of a deal, I would just go ahead and round that to 21. And then I'm going to look for my acceleration. So acceleration equals, what is my numerator going to look like here? 21 minus 0. It's going to be 0 minus 21. That's really important. So that gives me an acceleration of negative 4.2 meters per second squared. Okay, I was slowing down in the positive direction, so my acceleration came out negative. Right? Slowing down, they're going to be opposite signs. It's really, really common mistake for people to just go, okay, yeah, velocity over time gives me 4.2, right? But they miss that whole segment where it's 0 minus that. And so we got to make sure that we include that so that our acceleration comes out negative there. Okay? With somebody around you, I want you to try to come up with a scenario to answer this question. If the acceleration of an object is 0, does that mean the velocity is 0? So come up with an example or an answer to that with somebody around you. I would agree it's no. What's an example of that? Constant velocity, right? If I have my cruise control set, my velocity is not necessarily 0, but my acceleration is 0. I'm not speeding up or slowing down. What would be the case in which they are both 0? When I'm at rest, right? When I'm not moving. Good. All right, very good.
Stopping or coming to a rest look like on a velocity? Is it just stops?
On a velocity versus time graph. If I was going to come to rest, it would look like this, and then my graph would just continue along the x-axis.
Okay.
Yep.
If it were to do like a sudden stop?
Yep, so my slope would be as steep as it can go, right? Because it's going to take me a little time to come to a stop. right? Because we can't stop on a dime, right? So it's going to take me, it would just be a steeper slope when I'm coming to a stop quicker, and then I'm resting. Yep, good question.
Question.
Yep. All right, here we go. We're going to get our first kinematic equation, okay? These are what I call the big three. Right? Kinematic means motion. So these are equations for motion. And for these equations to be true, we have to have constant acceleration. Okay, for them to be true, we have to have constant acceleration. I'll explain what that means here in just a second. But on your equation sheet, I would just label these as, these are your kinematics. And then you're going to have three of them that list underneath there. All right, so when I say that these have to have constant acceleration, what I mean is that if we have a situation in which a car speeds up and then slows down and then does a bunch of different things, we can't solve that in one equation. We would have to break it into its parts to be able to solve. So that's all that means. It has to have constant acceleration for that time period. Okay, so if we say it speeds up, then it stops, then it slows down, then it does all these things, we have to break that motion into parts that we can manage. Okay, that's really all that means, okay? So here's our first kinematics equation, VF equals VI plus AT. You will notice, maybe, if we rearrange the equation we got previously, if I rearrange that equation, they're exactly the same. They solve exactly the same way. So times T plus VI gives me VF equals VI plus AT. Right? It's the same equation from the one we just got. So there's no need to have both of them on your equation sheet necessarily. This is the version I would tend toward and I would use more often just because I'm more comfortable with that being part of the big three. But you in reality could use this or the one we got previously and it would work just the same. Okay? Yep. You have to be careful with a T and a plus sign. Right? I try to make my plus signs really little and I try to give my T a little tail, but yeah, it's hard because they'll be next to each other in equations kind of often. So yeah, just be careful about what those look like.
And that's acceleration.
Okay, this equation got bumped down. I don't know why on the PowerPoint here, but it says a bus is traveling 30 kilometers per hour, speeds up at a constant rate of 3.5 meters per second squared. What velocity is it at 6.8 seconds later? So we're going to, again, keep making our list here. Okay, I like to make a list of my variables just to give myself a little organizational system. The bus is traveling 30 kilometers per hour. Tell me what variable does that represent for me? Initial velocity, good. And do you think I want to keep it in kilometers per hour? No, I want to go ahead and convert that, right? Because my acceleration is meters per second squared. So I'm going to divide that by 3.6. And that gives me about 8.3 meters per second. All right, the next thing it gives me is 3.5 meters per second squared. What variable does that have to represent? Acceleration. I know that because of the unit alone. Okay, it didn't ever say the word acceleration, but I know that from the unit that is the acceleration. And then the time would be 6.8. What velocity is it at? So that means I'm solving for, yep, and final velocity. And so I give that a question mark. I like to go ahead and write out what am I solving for? Because when we start doing problems that have 8, 9, 10 variables, we need to know and have a focus on where are we going, right? I want that question mark there to show me what am I solving for. Okay, so if I go back to that equation, the first kinematic equation that says VF equals VI plus AT, do we have a spot for all these numbers and my question mark? Does this equation fit with that? Yes. Okay, so I'm going to go ahead and just plug in then. VF equals VI plus A times T. And I'll go ahead and solve to find out there. What do you expect to happen to the velocity? To get bigger or smaller? Bigger. Yeah, because we're speeding up. So my final velocity there is, I got about 32.1 meters per second. All right, and my units would just be meters per second, not meters per second squared. Right, you can give yourself a little bit of a walkthrough here as well. If I know I'm speeding up at 3.5, 8.3 plus 3.5 is 11.8, right? And then another 3 is around 14, and then another 3 is around 7. I mean, you can kind of walk yourself through that just to be able to think about what that final velocity could be. Not that you necessarily have to, but it gives you an idea. Nope, because we converted this to meters per second, and our acceleration is meters per second squared. This is seconds. This is meters per second. We want them all to be consistent throughout that problem. So we could not plug in my initial velocity if it was kilometers per hour. It has to match. Yeah, good question. All right, here's our second kinematics equation. I don't know why it got cut off, but it did. So here's our second one. X final equals X initial plus VI times time plus 1/2 AT squared. Okay, that's the second kinematics equation. Okay, on this one, it's important to know that just the T unit, just the T variable is squared. Okay, the parentheses won't be included there, but we just need to see that the whole 1/2, that whole, it's not like this whole term is multiplied and then squared. It's just T. Okay, that gets squared by itself there. Okay, it's just that. All right, this down here, it says most of the time X sub I can be set equal to 0 since it's our starting location. That's a really helpful piece of information, right? I don't care what happens before the time interval that I'm looking at. So this most of the time is set equal to 0. Okay, so we are going to be able to drop that out of our equation a lot. Yeah.
What does X stand for?
X is displacement. Yep, so we would always measure these in meters, right? Those would be meters. Okay. What variable is this equation missing? Out of the variables we've looked at so far, which one's it missing? Final velocity. So this would be an equation you would use if your problem didn't give you any information about final velocity, right?
Would the initial just be any velocity that says it's going at this velocity? That would be initial.
Yeah, most of the time. And usually you just have to use context clues to figure out what's initial, what's final. But if it doesn't give you any information about it, we use this one a lot for vertical problems. If it says it's dropped off a cliff or thrown off a cliff and we don't know how fast it's going, we can solve a lot of information without having to know how fast it's going at the end. Okay? All right, here we go. A train accelerates from rest at a constant rate of 3.15 meters per second squared for 1.57 minutes. How far does it travel in that time? Okay, a couple context clues that we have to look at here. If it says from rest, what's that tell me about my initial velocity? It's 0, right? Initial velocity in this case is 0. It accelerates at this 3.15, so that would be A, right? It gives me that information pretty clearly. And then it also tells me my time. Can I keep that time in minutes? I can't. I need to convert because my acceleration is per second squared. So I'm going to go 1.57 minutes. And to get that to seconds, I'm just going to multiply by 60. Right? I don't need to draw out a whole T-chart. I can just multiply that.
And then do you want us to square it already?
No, I would wait until you for sure know what kinematic equation you're going to have to use.
Oh, true.
Because a lot of the challenge in these problems is trying to really figure out, well, which equation is going to fit, right? Eventually, you're going to have all three, and you're going to have to, based on your list, get a feel for, well, what am I missing? What am I looking for? And all that kind of stuff. So, yeah, I wouldn't do any math preliminary to that. So, I got 94.2. Is that similar to what you had? Okay. How far does it travel in this time? So, what variable am I looking for? Good. Yep. X final is my question mark. And I still, to this day, when I solve problems, I make this list. I think it's important. And I write out my question mark. What am I solving for? What is another thing I know to be true about X initial? It's 0, right? We're going to ignore whatever happened to the train before that 1.57 minutes. I don't care. I only care about what happened during that time interval. Yeah.
In what circumstances would X initial be?
I can think of very few, like 0.1%. I almost never do I have an initial displacement. Even if like we've done this, we've talked about this example. I'm on top of some cape, I'm on top of something, and I throw the ball down. Ball goes down here. Some people restructure their origin to look like this, in which case my initial height might be 10 meters. But I don't like to do that. I like to make this starting spot my origin. So my starting spot is always 0, right? And then my final displacement would be negative whatever, however tall the cliff is. Does that kind of make sense? So I like to choose the origin where my motion starts from for this always to be true. Okay. Yeah, Christina.
How would you tell like which kinematic equation?
Okay, so if I'm looking at my information right here, I only so far have one kinematic equation that has X final in it. Right? Look at your kinematics equations that you have right now.
Yeah, but why wouldn't you use
Which one?
the VF equals VI plus
So what would I solve for in that case?
the velocity final?
Okay, I could, but does my question ask me for that?
Oh
No, and so that I just don't need it. But yes, what you're saying is true. I could use and solve for final velocity, but if I don't need it, I'm not going to bother doing that, right? The way I'm going to figure it out is what am I solving for? And I usually have 2 equations to choose from. Sometimes 3 if you have to solve for initial velocity, because that's in all 3. But usually I can choose from 2 and figure out, well, what am I missing and what do I need to solve for and which equation fits that best? Okay. So I'm going to go X final equals 0 plus VI times time. Do I need to bother plugging in 0 times 94.2?
no.
No. Okay. So then we're just going 1/2 A times T squared. And I'm just going to square that time.
Can you also not? Do you have to can you skip the 0 plus 0 part?
You can not, yeah, you don't have to write those in if you want to. I'm just for our purposes right now putting those down. So X final, I got a pretty large number, 13,970. I'm going to round that up, 976. And what would my units be in this case? If this is a displacement. Meters, good. And so were we expecting our displacement here to be positive? Are we moving in the forward direction or the negative direction?
Forward.
Yeah, we assume positive. It didn't give us any indication to think otherwise. So we assume positive direction, which means our displacement should be positive. Okay. I would say it's a common mistake for people to just plug in the time as 1.57. It's just an overlook thing, right? But we've got to be really consistent about our units. Okay, are we feeling good? Easy so far? Nice and simple?
One more.
Love it. One more. Do you want to try this one on your own? This one is going to ask us to do 2 parts, okay? In an emergency, a driver brings a car to a full stop in 4 seconds. The car is initially traveling that when the braking begins. What is the car's acceleration, and then how far does it travel before coming to a stop? So you will have to do this question in 2 parts. Okay, so that's the hint I'm going to give you. Okay, last one is VF squared equals VI squared plus 2A delta X.
It looks so weird on mine.
I don't know. Yeah, did it print on your paper fine?
It looks like it's V2 over F.
Oh, really? Okay. Yeah, I don't know what the deal is. It didn't import those very well into this. I'm not sure why. Be true. What do we know to be true about X initial most of the time, right? If this is X oops, that's x final minus x initial. And we know this is most of the time 0. Do we need to bother with that? No. So most of the time, in all reality, that's just x final, right? That's really what it's going to be, okay? There might be situations where we have an x initial, but it just doesn't happen that often. So I'm okay if you just understand that most of the time we drop that out of that equation. The one thing I do want to remind us of, if we have to solve for either of these, vf squared or vi squared, right? I don't want to solve for vf squared. I want vf, right? Just final velocity. So if I take the square root of vf squared, that would give me vf, right? I need to take the square root of that number. So let's say that if I have to take the square root of a number, what's the true answer? If I take the square root, let's say of 16, the actual answer is not just 4, it's plus or minus 4, right? Because we don't know whether the original one was positive or negative. So that is the same case for velocity here. So this is the only scenario in which we have to add the sign, plus or minus. We can't just trust the math here because we have to know what direction it was going. So if we have to solve here for final velocity and our object was moving forward, we would choose the plus. If we were solving for final velocity and, like, let's say our object was moving downward, then we would choose the negative, right? We have to add that on there. Yeah, Macy.
So this is kind of similar to the first equation, but this equation doesn't have the time.
Exactly.
So it'll give us time, this is what-
Yep, exactly. Each equation is missing something. First equation doesn't have any displacement. Second equation doesn't have final velocity, and third equation doesn't have time. So now you have flexibility about which ones you can use based on the information given. So yeah, no time in this one.
And we assume initial velocity is going to be 0.
Not always. Nope, it's not an assumption that we can make. Nope. Okay, this one says a car starts from rest, so that's an assumption that does ring true in this problem, right? Velocity initial is 0 here. VI equals 0. Speeds up at a rate of 3.5 meters per second squared. So A equals 3.5. After the traffic light turns green. How far will it have gone when it's traveling 25 meters per second? So give me some insight as to what are we solving for here? What variable is going to be our question mark?
The distance.
So x final is my question mark. And then it says when it's traveling 25 meters per second, that has to be my velocity final. Would we agree there? Okay, so now I'm going to take a look at all of my information. I'm solving for x final. So out of my kinematics equations, I have 2 options that have x final in them, right? The second or the third. So now I have to figure out, well, which equation fits my situation best? I think the third one, because I'm not given any information on time, and the third one doesn't have time. We agree? So we're going to go 25 squared equals 0 squared plus 2a. And then I know my x initial is 0, okay, per usual. And so I'm actually just going to plug in x final there. I'm not going to bother with the delta x because I know it's whatever my x final is minus 0 anyway. So I don't need to plug that in. Okay. And so now I'm just going to solve, right? 25 squared, I know is 625. And 3.5 times 2 is 7. XF. So I'll take that and divide it over. And we get an x final equal to 89.3 meters. Okay. Even though I'm starting from rest and speeding up, I'm moving in the positive direction. So I know my displacement here is positive. Now, answer this question. Let's say you were given this exact scenario. Okay, you're given all this information. Would it have been valid for me to solve for time using the first and then solve for x final using the second kinematics equation? Would that have worked? Right? I could have used this this, and solved for time. And then I could have used all that information to solve for x final from the second. That would have worked fine. That happens sometimes, that you overlook something and you do extra work. But who cares? It gets you to the final answer. There's a lot of pathways to get to our final answer. I'm usually going to try to show you the shortest, but there are lots of ways to get from start to finish. So don't feel discouraged if like you did a little extra work, but you still got there. Fine, right? I'm always looking for the path of least resistance, but if you have to wonder your way to it, that's okay too, right? You just might have done a little extra. Okay, are we feeling okay? All right, I'm going to skip ahead just a couple here to a little bit more of a problem-solving type question. We'll see how this goes, okay? This says you're designing an airport for a small plane. So this is like 3 or 4 slides ahead, so you can kind of jump in your notes. You're designing an airport for a small plane that must reach a speed of 27.8 meters per second before takeoff. The plane accelerates at 2 meters per second squared. If the runway is 150 meters long, can the airplane reach the proper speed to take off? So I'm not going to give you any hints about how to answer the question. I'm going to let you work through whatever pathway works best for you. Okay, and then we'll talk about it or debrief here in just a minute. Right, my process was thinking about if I have to reach this speed, I want to know what distance is it going to take me to do that. And then I can check, is it long enough or is it short enough? Did anyone go about it a different way? You guys said you solved for time first, but then you still ended up solving, did you still end up ignoring the 150?
I did.
Yes, I did. I ignored the 150.
Okay.
Because after I was like, I don't think we really need it. And then we just look at our answer that we get.
Okay. How did you go about it? That's the type of problem that just asks you to not be so narrow focused on the numbers in the problem, right? I had probably the quickest way about it is to ignore one of the numbers, whether it was velocity or whether it was displacement, and use that as a checkpoint or like a guide point for you. So that's my plea to you, not to get too wrapped up in the numbers and to take a step back and think about what's the big picture? What type of question am I trying to answer? And then to go about that. But I put this question in on purpose because I like us having to work our way, lots of paths to get to our final answer there. Okay? All right. So the next slide did ask us what, and so, right, it needs to be at least that long. Yeah, I don't know. Any questions with that? Does it need to be